오늘은 그러면 Continuous Time Finance에 대해서 좀 얘기를 해볼까 합니다. 먼저 Continuous Time Finance를 이해하려면 Continuous Time에 필요한 수학적인 배경들을 알아야 돼요. 그리고 이 수학적인 배경이 보통 Continuous Time Finance에 대한 진입 장벽이 되는 경우가 많거든요. 그래서 오늘은 제가 최대한 Continuous Time Math를 Continuous Time에 필요한 수학을 쉽게 이해할 수 있고 또 인투이티브하게 이해할 수도 있도록 최선을 다해서 한번 설명을 해보도록 하겠습니다. So today's lecture is about continuous time math. Continuous time math is a necessary tool to understand continuous time finance. Sometimes it's very difficult, especially for people who get exposure to continuous time in the first place. So I will try to make it very easy and very intuitive so that you can understand and use continuous time math in real life applications. 자, 그러면 화면을 쉐어해 보도록 하겠습니다. 자, 먼저 Continuous Time Finance를 이해하려면요. Brownian motion을 이해하셔야 돼요. So what is Brownian motion? Brownian motion is after the following process. So it is sometimes used using the notation Z, sometimes using the notation W. Okay? And ZT is actually a random variable with mean 0 and variance of t. 먼저 이해하셔야 될 점은 이 GT라는 랜덤 베리어블 제가 어떻게 표현할 수 있냐면 이제 이렇게 시간이 움직이고요. 또 랜덤 베리어블이 이렇게 있는데 그 랜덤 베리어블의 레벨이 GT죠. 이 랜덤 베리어블의 평균은 항상 0입니다. The unconditional mean of ZT is always 0. Another thing you need to know is the variance of ZT is T. So these two are the first characteristics that you need to know. 먼저 이 성질들을 아셔야 되고요. 두 번째 성질로 알아야 될 것은 GT와 GS라고 할게요. GS와 GT 마이너스 GT와 GS. 예를 들어서 T가 S보다 큰 거죠. For example, if you consider two points in time, time S and time T, and S is greater than T, so T is the future time, S is the past. The Brownian motion value measured at time S and the change that occurred during the time from S to T, which is ZT, so that the difference is ZT minus ZS. So these two are always independent. So what happened up until time S and the change from S to any time is going to be independent. Okay. 자, 그 프로퍼티를 나타낸 게 바로 여기 있는 이 수식이에요. 지금 무슨 말이냐? 이 수식은 타임 t까지 있고 그 다음에 타임 t 플러스 델타라는 So we are assuming delta is a very small number. So time t에서의 observation zt and the next observation which is zt plus delta t 이 둘 사이의 difference가 항상 mean zero이고요. mean zero and the standard deviation of delta squared. Another way to understand this is, so this is a shock. This is a shock, so you can call it epsilon, and this epsilon t is a normal random variable with mean 0 and variance of delta. So the time difference between the two Brownian motion is going to be the variance of the difference. So that is the first property that you should know. 자, 그 다음에 알아야 될 두 번째 property는요. 이 dz, so we will make delta very small. Okay? In other words, delta is going to approach 0. 이 time difference t 플러스 델타와 t 사이의 time difference를 아주 작게 만들 겁니다. 아주 작게. 아주 작게 만들 때 이 dzt는 어떤 성질을 띠느냐? square root of dt와 같은 오더로 움직여요. 그 말은 무슨 말이냐면 dzt is going to approach 0 at the same rate as square root of dt. 즉 극한에서의 성질이 square root of dt의 제곱근과 같은 성질을 띠게 됩니다. 이 성질이 어떤 식으로 나중 계산에 영향을 미치는지는 뒤에 있는 예제들을 보시면 알게 되실 거예요. So in other words, the rate at which dzt is approaching 0 as dt becomes 0 is the same as the rate of square root of dt. Therefore, we have the following important properties. 따라서 어떤 일들이 벌어지냐면요. dct를 제곱을 하면 dt와 같은 order of magnitude가 됩니다. 그게 여기 있는 property예요. 즉 무슨 말이냐? 보통 극한값을 계산할 때는 dt를 제곱하면 어떻게 되죠? dt는 보통 0으로 간다고 우리가 생각을 하잖아요. 그런데 브라우니안 모션의 차이는, 즉 dzt는 신기하게도 제곱을 하면 0이 되는 것이 아니라 dt가 되게 됩니다. Because of the property here, because of the property that dzt behaves like square root of dt, when you actually square dzt, what you obtain is dt instead of 0. But for other infinitesimal differences, for example, dt, when t is a scalar number, this approaches 0. There's also another property that is important, which is because dt, when it's squared, it becomes 0. So when dt is also multiplied with dzt, this also becomes 0. So these properties will be important in calculating the examples that will be shown later. 자, 이것들을 먼저 좀 지우도록 할게요. So next two properties are also very important. Next two properties. So what are they? 먼저 dzt. What is dzt here? So dzt is basically z t plus dt minus zt. And this works like random variable with mean 0 and variance of dt. So 앞에서 본 대로 이런 discrete time에서의 example을 본다면 DGT는 사실 T와 DT 사이에 있는 두 브라우니안 모션의 차이로 볼 수 있고요. Of course, DT is approaching zero, that is implicitly assumed. 그리고 이 두 브라우니안 모션의 차이이기 때문에 평균이 0이고 베리언스가 DT인 랜덤 베리어블과 같아요. 따라서, therefore, what properties do we have here? So if we take the mean of DCT, what we get is basically 0. There's also other important property. Variance of DCT. I forgot the conditional. So conditionally is 0. In other words, so I forgot to explain about the conditional property here. So of course, the unconditional average of DZT is 0. And you can see that from the following manipulation, right? So unconditional property, unconditional expectation is it's going to be like this. And what is the first term? First term is basically average of normal random variable that has the variance like that. So that's the first term. And the second term is normal random variable with mean 0 and variance of t. 따라서 둘 다 0이니까 0 마이너스 0에서 0이 되죠. Therefore, unconditional expectation of DZT is simply 0. But what we are interested here is the conditional expectation. So how does that become? The following, the property over there. So let's calculate the conditional expectation. Now, conditional expectation of DZT. So if you simply plug in the expression above, and this is what we get. And the expectation operator is linear, so we can divide the terms into two. We can separate them out like this. 이렇게 할 수 있죠? Now, given the time t information, the expectation of the Brownian motion is always zt. Minus, in a given information zt, simply zt. So it becomes 0. 이게 왜 그러냐면요. 타임 t에서 t 플러스 dt까지 했을 때 gt라는 레벨이 있고 그 다음에 GT에서 DT로 가잖아요. 여기서 GT에서 여기로 얼마만큼 갔는지 이게 normal random variable with mean 0 and variance of DT. Right? Because the difference between the two Brownian motion follows the mean 0 and DT, that means that expectation at this becomes simply 0. Okay? Therefore, we obtain the equality above. 자, 그 다음에 그 다음 property를 봅시다. So the next property says the variance, the conditional variance of the dzt, okay, and we can express it in terms of the usual manipulation, like this. 이렇게 할 수 있죠? variance니까. 그런데 물론 여기 있는 이 오른쪽에 있는 이 텀은 0이고요. What we'll end up with is dt, okay? Because of what? Because of the property here. Therefore, this becomes dt. Why? dt is just a number. There's no randomness. Time is a constant or is a deterministic number. Therefore, there's no randomness. Expectation of dt is simply t. I forgot time t subscripts. So these are the key properties of the Brownian motion that you really need to know. 자, 정리하면 dzt는 normal random variable mean zero and variance of dt and expectation of the expectation of 이런 경우는 어떻게 쓸 수 있냐면요. t가 t보다 큰 경우나 즉 오늘 시간에서 봤을 때 미래의 브라우니안 모션에 대한 평균값은 이렇게 나타낼 수 있습니다. So we can express it in the following way. 이렇게 할 수 있죠? And what is the average of this thing? This is basically zero. Basically zero. Why? The difference in Brownian motion is a mean zero random variable. And the second term is d. So these are the important properties that you need to know. And you can do similarly also calculate the following, the time t variance of zt. How can you do it? In the same fashion. 이렇게 할 수 있죠? 똑같은 숫자를 빼주고 더해주고. 그런데 in a given time t information, this is just a constant. So you can just ignore it. 이렇게 되고요. And we know that the difference in two Brownian motion is a normal random variable with mean zero and variance of t minus t. Therefore, this is simply t minus t. So these properties you should be very familiar with, and you should be able to drive it in any time. 자, 그러면 다음 diffusion process로 가봅시다. diffusion process는 뭐냐면 주어진 브라우니안 모션에서 이렇게 파생된 프로세스들을 얘기하는 거예요. 그래서 one good example is the following. There's some process xt, and we will express xt in terms of its difference. So in other words, dt can be thought of as xt plus dt minus xt. in a very small time interval the difference in the value of the process. 자, 이거를 어떤 식으로 나타낼 수 있냐? 예를 들어서 이렇게 나타낼 수 있어요. 이걸 어떤 식으로도 볼 수 있냐면요. discrete time 모델에서 이렇게 쓸 수 있잖아요. 즉, change in delta xt plus 1이 어떤 constant term이 있고 plus sigma epsilon t plus 1 이런 discrete time에서 볼 수 있는 프로세스의 즉 대칭하는 경우라고 볼 수 있어요. 자, 이런 경우를 우리가 뭐라고 부르죠? 잠시만요. 이런 경우는 우리가 보통 random walk with drift, random walk with drift랑 똑같은 경우예요. 즉 이런 diffusion 프로세스는 이 diffusion 프로세스가 random walk with drift랑 똑같은 경우예요. In other words, suppose there's a process xt. xt can be expressed in terms of its difference using d. And if the process is expressed in this way, that is identical to the case of the random walk with drift. 자, 이런 경우에 conditional expectation of dt, let's see what it becomes. Conditional expectation of mu. So I'm actually looking at the expression here. Conditional expectation of mu dt plus sigma dzt. And because mu dt is a deterministic term, it will come out like this. And we have sigma times dzt, and we know if you take the expectation of a dzt when zt is a Brownian motion, then you get 0. Okay? Therefore, the conditional expectation of dxt is simply this term here. 똑같습니다. 이걸 discrete time에서도 볼 수 있어요. 어떻게 하냐? 델타 xt plus 1 이렇게 되겠죠? Conditional expectation of mu plus expected value of t plus 1. This is simply mu. 왜 여기에는 dt가 없고 왜 여기에는 dt가 있고 왜 여기에는 dt가 없을까요? 왜냐하면 discrete time 경우에는 dt가 1이죠. 1. 이렇게 됩니다. So this is the derivation for the case of the discrete time situation. So conditional expectation of delta xt plus 1 is simply mu. And there's no dt, whereas there is dt here. The reason is that dt in the discrete time case is simply 1. 비슷한 방법으로 여기에 있는 conditional variance를 구할 수가 있어요. 이 conditional variance of dxt 어떻게 되는지 봅시다. 이렇게 되죠? 그런데 여기서 우리가 또 알 수 있는 사실이 mu dt는 deterministic한 텀이잖아요. 이미 알려져 있는 숫자이기 때문에 컨디셔널 베리언스를 취하면 그냥 0이 돼요. 0. 우리가 고려할 필요도 없습니다. Now is variance, conditional variance of sigma dzt, which is sigma squared, variance of t, zt, which is sigma squared times dt. 이렇게 되죠. 따라서 여기 있는 게 나옵니다. 마찬가지로 이거를 똑같은 식으로 discrete time으로 할 수도 있어요. So in English, the variance of dxt is simply sigma squared times dt. And the reason is, first of all, the constant term here, deterministic mu times dt, is going to disappear. And we use the property that the variance of dzt is simply dt. 자, 그 다음에는 so in a discrete time case, what does it become? The math is the same. The concept is basically the same, right? You can view it as a discrete time case. In that case, variance t of mu plus sigma epsilon t plus 1. And this mu is just a constant, so it is going to, it doesn't have any effect, and therefore you have variance of t, epsilon sigma times epsilon t plus 1, which is sigma squared times variance of epsilon t plus 1, which we assume is 1. Okay? So it's just sigma squared. Okay? So we have basically the same situation in discrete time and also in continuous time. So understanding the analogy between the discrete time and the continuous time is very helpful. 그 다음 밑에 있는 이 example들을 좀 볼까요? 예제들을 봅시다. Let's take a look at these examples. So the first case is you will see this case very often. The quantity on the left-hand side is actually net return. Okay. How do you see that? PT가 가격이라고 할게요. PT 가격. 주가라고 볼 수 있죠. PT is the price or 주가. So when PT is the price, PT plus 1 minus PT is a change in price, and we will use, in a continuous time case, it is going to be the PT. Therefore, net return is simply, we are assuming no dividends here. 배당이 없다고 가정할게요. This is the net return, right? And in the continuous time case, this is simply expressed in this way. Okay, so on the left-hand side here, in this example, we have net return. Okay? On the right-hand side, so what do we have here? 이거를 discrete time으로 써볼게요. So if you express it in discrete time, on the left-hand side, you have the net return equals mu times sigma times epsilon t plus 1. Okay? 즉 무슨 말이냐면 net return이, 즉 어떤 주식이 있을 때 net return이 어떻게 되냐면요, 그냥 constant가 있고 net return이 그냥 constant란 얘기예요. net return constant. Conditional expectation is a constant. 이런 경우 우리가 뭐라고 부르냐? We call such case as a geometric Brownian motion. So this is the geometric This is what's called the geometric Brownian motion. Oops. This case is the geometric Brownian motion. So in a very simple geometric Brownian motion, we have net return on the left-hand side, and on the right-hand side, we have the expected return plus the shock, the noise. So in other words, if you simply take the conditional expectation of the net return here, then it's going to be mu times dt plus the conditional expectation of sigma times dzt, which we know is 0. So simply is mu times dt. In other words, in a very simple geometric Brownian motion that is given here, the expected return is simply a constant, mu times dt. 자, 그 다음 케이스 봅시다. Next case. This case is what is called the Ar1 case, okay, or mean reverting process. Mean reverting process. Okay, so why is that called that way? Again, let's take a look at the discrete time analogy here. dxt is again xt plus 1 minus xt. Let's just call it delta xt plus 1. That is equal to negative of phi xt minus mu. dt is, in a discrete time, is going to be t plus 1 minus t. So this is simply 1. So dt is simply 1 plus sigma times epsilon t plus 1. Okay. So if you arrange it, then you can see why this is the Ar1 case. Okay. Therefore, right, so this is Ar1 process with Ar1 parameter being 1 minus phi. You can also interpret this equation directly, right? This expression in a more direct way. The change in the next period. So if you have a process, the change in the next period here is going to be determined by how far the process is from the mean. So mu here is the average of the process. So if the current level of the process is higher than mu, which is the mean, okay, then it will mean revert. It will revert to the mean. And if the current value is lower than the mean, it is going to again approach to the mean, right? So if xt plus xt is lower than mu, okay, so that this is the average level of mu, and xt is lower, right? Then xt is going to increase in the next period. Why? Because xt minus mu is a negative number minus, so it's the positive number, right? So delta xt plus 1 in the next period is going to be positive. And this phi, in this sense, measures the speed of mean reversion. Okay. Phi is the speed of mean reversion. Okay, so we have seen the geometric Brownian motion and also the Ar1 process. Now, next very important thing to know is the Ethos Lemma. Ethos Lemma is very, very useful to get the, basically this is the chain rule in stochastic calculus. So suppose you have a function y, which is given as, okay, two variables, right? Then how do you get the total derivative of y? That's going to be f, and because it has two arguments. And there's also higher order term, but higher order terms are assumed to be 0 because in a deterministic case, dt times dx is assumed to be 0, right? Okay. In a deterministic case, infinitesimal change in t and also the infinitesimal change in x, when you multiply them, they become 0. But in the stochastic case with the Brownian motion, that is not the case. Why? This is no longer true because dx is like, oh, this, well, I'm sorry. This is still true, but in a deterministic case, dx squared is 0. Okay? But in a diffusion process case, Brownian motion case, this is not true, but instead dx squared is dt. Okay? dx를 제곱하면 dt가 되기 때문에 거기서 이토 렘마가 deterministic한 케이스와 다르게 되는 겁니다. Then how is that going to be different? So suppose you have x is given as a diffusion process, meaning it can be any diffusion process, and you want to suppose y is a function of x and t. Then what we are interested in is to get the value dyt. Okay? So how do we do that? That is the thing. So basically the math is almost the same as before in a deterministic case. So that's d of f t and xt, right? And in a deterministic case, first you take the partial derivative with respect to t and you multiply dt. And also there's a partial derivative with respect to x and dx. And that was it for the deterministic case. But for Ethos Lemma, because dx squared is no longer 0, we have the second order term here. Okay. Then 자, 여기서 그러면 먼저 dx 제곱을 한번 계산을 해봅시다. Let's calculate dx squared. Because dx is mu dt plus sigma dzt, and we are squaring it, then it becomes mu dt squared plus sigma dzt squared times 2 times mu dt times sigma dzt. 자, 여기서 뭘 할 수가 있죠? This term becomes 0. That term is also 0. Why? Because we know that dt times dzt is 0. The only thing that is not 0 is this thing here. In other words, this thing becomes sigma squared dt. Now we are plugging in for dx squared here. Then we have the Ethos Lemma. Ethos Lemma is going to be given like this. Now dx, let me change the color. Okay. 자, dx는 어떻게 되죠? So we substitute dx here. dx is mu times dt plus sigma dzt plus a half second order derivative of x times dx squared, and we know dx squared is sigma t squared dt. Now you rearrange the terms here, then you get the expression up here. 자, 키는 무엇이냐면요. 그래서 키는 이토 렘마는 보통 수학에서 해주는 전미분이랑 똑같아요. 무슨 말이냐? dy를 구하는데 y가 t와 x의 함수다. 그러면 먼저 t에 대해서 편미분을 취해주고 x에 대해서도 편미분을 취해주고 거기에다가 dt와 dx를 각각 곱하면 되는 거예요. 그런데 여기에 텀이 하나가 더 붙습니다. 이 텀이 하나가 더 붙어요. 왜 그렇죠? 왜냐하면 dx의 제곱이 더 이상 0이 아니거든요. dx의 제곱이 더 이상 0이 아니야. In a deterministic case, dx squared was 0, but in a Brownian motion, dx squared is no longer 0. So that term should be included. And that is the only complication with Ethos Lemma compared with the previous cases, compared with the deterministic case, I'm sorry. Okay. Now, let's moving on to solving the stochastic differential equations. Let's take a look at some simple cases here. 그냥 여기다가 풀죠. 자, 이걸 보겠습니다. 자, 먼저 dxt가 suppose the case when dxt is simply mu dt plus delta dzt. Okay, so this is the most, the simplest case that you can imagine. Now we want to take the integral on both sides, from 0 to t, from 0 to t, from 0 to t. Okay. Then what does it become? Basically, dxt is the difference between xt plus dt and xt, right? So if you do the integral of these changes, then what you get is basically the last term, xt minus x0. So this is xt minus x0 equals, mu is a constant, mu is going to come out, times the, if you look at the second term, it's the integral from 0 to t dt, and we know that is simply t minus 0. And the last term is the same. In the last term, sigma times zt minus z0. Okay? So we have what we got here. There's another way of viewing this. Suppose, let's just translate it into a deterministic case. Okay. 이렇게 되죠. 자, 양변을 다 0부터 t까지 서메이션을 합시다, 양변을. So if you sum the both sides from 0 to t, then what do you get? T minus 1 is better. Okay, and then you get xt minus x0 on the left-hand side, and mu times t. Okay, so you're adding mu by t times. From 0 to t minus 1 is t times. Okay? So mu times t plus sigma times, you have to add all the shocks that have accumulated this way. And this is simply the Brownian motion, because Brownian motion is a random walk. This is a random walk. Okay. So in a sense, solving a stochastic differential equation is similar to adding out all the differences in a given equation. Okay. So these are the simplest case that is possible. The more complicated case is when the process follows the geometric Brownian motion, right? So this is geometric Brownian motion case. Okay, so let's see how that changes with the geometric Brownian motion. Mhm. Okay. Now dxt equals xt equals mu dt plus sigma of dzt. We cannot use the same technique as before by just integrating out on both sides. Why not? Because the ones on the right hand side you can integrate out. That's easy. But this is not easy because in a discrete time analog, this will be like sum from 0 to t minus 1, and this is not possible. I mean, it is possible, but there is no closed form solution. So what we do instead is the following. Instead of taking the integral directly, what we will do is there's a well-known trick. So let's just suppose we begin from log of x. Okay? And let's take the derivative of log of xt. Okay, log of xt. Now, how do you take the derivative of log of xt? How do you do that? Here we use the Ethos Lemma. Okay? So what is Ethos Lemma? It's the same as taking derivative of some deterministic number, say y. How do you take the derivative? Becomes like this, right? So it is the same as in the deterministic case, except we have to consider the second order derivative case. So let's apply the Ethos Lemma. And let's apply Ethos Lemma. So we have xt times, so there's no t here, so delta dt is simply 0. We don't have to consider. So the only thing we need to consider is and these two things, right? So let's just first do the first one. Okay? So by taking the derivative with respect to x, we have 1 over xt times dxt. Okay? But then there's the Ito term. Plus half times the second derivative, which is okay. And it becomes 1 over xt times dxt plus minus, because there's a negative sign, minus a half 1 over xt squared times dxt squared. And how is dxt squared calculated? Dxt squared is from here, mu times xt times dt plus sigma xt dzt, and you square it. The only term that survives is xt sigma squared times xt squared dt. Okay? So is sigma squared xt squared dt. Okay? So what we have is 1 over xt times dxt minus a half times sigma squared dt. Okay. So why do we do this? Why do we need that? Because once we have this, right? Once we have this, we have the following: d log xt is simply dxt over xt minus a half of sigma t dt. Now, let me arrange it one more time. dxt over xt is simply d log xt plus a half of sigma t squared. And now you can plug it into here, right? What do you get? Then you have d log xt plus a half of sigma t, sigma squared times t. That is going to be the same as mu dt plus sigma t ct. Now what is cool is that you can just take the integral on both sides. In other words, by taking the Ethos formula, Ethos lemma on log of xt, you got is the following here. And then what is cool is from there, take the integral on both sides, and what do you get? Let me erase it here. What do you get? You get the one on the left hand side, the one on the right hand side, and the integral, right? Well, actually, this thing is going to be the same as the zt minus z0. Okay? And then you just take the exponential on both sides and you get this formula. Now, in other words, for geometric Brownian motion, xt is the value of the Brownian motion after time t is going to be current time times e to the drift, and then there's negative sigma squared, a half times sigma squared term, times t plus sigma ct. So this is solving the geometric Brownian motion. So in the case of the log normal diffusion or geometric Brownian motion, we saw how the stochastic differential equation can be solved. The next example is the following. When the process follows the Ar1 process, let's also see how we can solve this equation. Now, it would be great if you can just take the integral on both sides. But in this case, it's also impossible to do that. Why? Because we have xt on the right-hand side, and that's going to be very, very messy. It is basically impossible. So what is the trick? The trick is that let's consider the following function. Okay? And we will take the ethos of it. Okay? So it's going to be the derivative of the first item times the second item, which is v times E phi t dt plus E t dxt plus v E phi dt. I'm sorry. T dt times dxt. Okay, so this is the Ethos term here. This is the one on the right hand side. This is the Ethos term. And we know this thing in this case is going to be 0. Why? Because we have dt. When dt is multiplied with anything else, it becomes 0. Okay? When dt is multiplied with dz xt, it is going to be 0. So we only need to care about the first term here. So we have v xt dt plus e to the pt dxt. Okay? So why do we do this? Because now you can see the trick here. Okay, so let's divide both sides by e to the negative. Let's divide both sides by e to the vt. Okay, then it becomes okay. Before we divide it by this thing here, let's rearrange this one. Okay, so if you rearrange it, then it's going to be dxt plus v xt dt equals v times mu dt plus sigma of d ct. Okay. Now multiply both sides by this. Then we have e to the vt dxt plus v times e to the vt xt dt equals v mu e to the vt dt plus sigma times e to the vt dzt. Okay. Now, can you see something familiar here? This thing is the same as that. So it becomes d of e phi t xt equals the same thing on the right. Okay? The good thing about using iPad is I can just copy, paste. Okay? Then you can simply integrate out both sides. Integral, integral, integral. Okay? Then you get integral from 0 to t. And you get e to the v t xt minus x0 equals, this is going to be mu e phi t minus mu plus okay. Now you solve the stochastic differential equation, and then you rearrange the things, then you get this thing here. Okay. Oops. Now this term here cannot be further simplified, and it should be left in this way. Okay, that was a mistake. Okay, so we have seen how the stochastic differential equations can be solved for the case of AR1. Now, with these solutions to the stochastic differential equations, it is really cool because now you can calculate the mean and the standard deviations. Let's first calculate the expectation of the log normal diffusion or the geometric Brownian motion. Okay? So how do we calculate the expected value of xt? How do we do that? Well, there are two things you need to note. First thing is, this one is deterministic. So it shouldn't affect in the calculation of the mean. The only randomness is here, but we know that this is simply, and it is a normal random variable with mean 0, and what is the variance? Sigma squared times t. Okay? So basically it is the case of, remember when from the last class, remember when there's a random variable x and this follows m times sigma squared of standard normal variable, Gaussian random variable, then you can calculate e to the x, which is, okay. Now the same trick is going to be used. And what do you get? Now this one here it's gonna become e expectation of x0 times, well, let me rewrite. Okay. So it is going to, so expectation of xt is going to be the first two terms here, this one and this one, they're all deterministic. So they will come out of the expectation operator. Okay. Then we have exponential of the last term here, but we know that that is a normal random variable with mean 0 and variance of sigma squared times t. Okay. Therefore, it becomes, using this formula here, okay, mean is 0 times a half times the variance. What do we get? We get this beautiful expression here. Oops. Okay. T. Okay, so the average of the geometric Brownian motion is simply given like that. You can also similarly calculate the variance of xt. Okay, variance of xt. That's gonna be your homework. That's gonna be your homework. Okay. Now, the case of AR1 process is a little bit different and it's more complicated, but it's also doable. It's also doable. Okay. Okay. Now, the first thing to do is take the expected value of xt minus mu. Okay, that's the expected value of e to the minus vt. I'm just rewriting the equation here, just plugging in, times x0 minus mu plus integral from s equals 0 to t e to the minus v t minus s times sigma dzs. Okay. How is this calculated? Well, the first term here, this is deterministic, so it will come out. Now, if you look at the second term here, this is deterministic. Sigma is also deterministic. The only randomness here is dzs. Right? Therefore, the expectation of this thing is going to be 0. It is similar to the case where, right, so you're taking the expectation of some okay, a discrete time case, and you can consider the case like this: sigma and epsilon s. Okay. And this is going to be the same as expected value of epsilon, and this is 0. Therefore, the whole thing becomes 0. It's the same principle. Okay. The other case is a little bit different. Now we are getting the variance of xt minus mu. Okay. And because the mean is this, so it's going to be the same as expected value of xt minus mu squared minus e of xt minus mu squared, right? And we have calculated this thing before in the previous case, right? So we will focus on this one. Or alternative way of doing that is, instead of using the variance in terms of the mean, variance is basically squared average of distance from the mean, right? Squared. Okay. And this is basically expected value of, using this fact here, using that. So this is the mean, right? This is the mean of the process because it's the same. This thing, that thing is the same. Okay. Therefore, it is simply s equals 0 to t e to the minus v t minus s sigma dzs and squared. Okay. And it is known that this is simply the same as okay, it is like this. Why? The reason is because if you think of this thing here, it is basically the sum between 0 to t e minus v t minus s d epsilon s times s prime oops, there should be no d's here. Okay. and you take the average of the entire thing. The key is that expected value of epsilon s and epsilon s prime when s and s prime are different, this is going to be 0. Why? Because s and s prime are independent. The same principle holds. So all the cross terms between s and s prime is going to disappear. The only thing that remains is that e to the minus v times s minus s times epsilon s times e to the minus v t minus s times epsilon s. Okay? So in other words, when s and s prime are the same. Okay? Therefore, this is e to the minus s t minus s squared times epsilon s squared. Okay? That is basically what is going on here. The thing that is inside squared times ds. Okay? I mean, this result is very general, in fact. Expected value of some stochastic integral of some function f, which is zs times zs squared is basically the same as the thing that is inside the squared s. Therefore, this stochastic integral becomes normal integration, and you can solve it like that. Right, that is it. And when you have time, practice. Okay? Practice all the calculation that I have done here.